This is the video guide that goes along with the classification of matter activity, which is also known as the pyramid of matter. And so that will give you kind of a hint as you're getting started as to what this thing's going to look like. Okay, at the top of my diagram, when we're classifying matter, we're going to start just with the broadest definition, so just all matter. And that's going to be kind of the top of our pyramid. By definition, matter is anything that has mass and occupies space. And so mass is just the measure of the amount of matter present, and then that occupies space, the scientific term for that is volume. So has mass, has volume. Okay, and as we go further down and we want to kind of narrow our definition of types of matter, you can essentially split all matter into one of these two categories. So all matter is either going to be a substance, and sometimes you'll see the term pure substance, or if it's not a pure substance, then it tends to be a mixture. So when you look at a pure substance, that is matter that is made up of only one kind of atom or molecule and has uniform and definite composition. So essentially what that means, this definite composition, that means that it's always made up of the same number and types of atoms. So they're in a fixed ratio. Like for example, water is always H2O. It's always 2 hydrogen and 1 oxygen. If it's any other ratio, it's not water. If you have, like H3O plus, that's a hydronium ion, not water. That's an acid. If it's OH minus, that's hydroxide. That's a base. If you have like H2O2, that isn't water. That's hydrogen peroxide. In order for it to be water, it has to be 2 hydrogens, 1 oxygen, and that's the only thing it can be. And then the next thing was the mixture. The mixture is essentially matter that is made up of more than one kind of atom or molecule. It's important to note that it is a physical blend of 2 or more substances. So a physical blend means that they are not chemically combined. It's just matter that happens to be different unique types of matter that are just sitting next to one another. They're not bonded in any way, shape, or form. They're not sharing electrons or gaining and losing electrons and sticking together by opposite electrostatic forces. We'll learn about types of bonding and electrons and so forth later. But just for now, be aware that when you're looking at mixtures, they are not chemically combined. It's just a physical combination, just things that happen to be interspersed with one another. And in continuing down with my pyramid, under pure substance, the first type of pure substance we have is an element. And by definition, an element is the simplest form of matter made up of only one type of atom. There happen to be, if you look up at the periodic table of the elements, in order for something to be an element, it essentially has to appear on that document. You may notice that right now there are 118 known chemical elements on that table. Just so you know, there are only 91 of them that are actually naturally occurring. All the others are synthetic. They're made by scientists in a laboratory, and we'll get more in depth with that later. But all those other things that you see that are printed on the table, those are elements. They have unique properties. And the other thing that you're going to find under pure substance is the compound. And compounds are made up of 2 or more elements that are chemically combined, and so that's important. That they are bound together through either, sharing electrons, gaining and losing electrons, something like that. And it's important to know that they are in a fixed proportion. We already kind of talked about that fixed proportion idea. But essentially what that means is that they have a definite formula. All right, so it's always made up of so many atoms of this first element and so many atoms of the second. And that's the only thing it can be. As a little side note, one thing that always amazed me when I was first learning chemistry, and actually it's still kind of neat when you think about it, is that properties of compounds and the properties of the elements that can make those compounds up are oftentimes very different. And I'll share a couple of examples with you. You'll notice this first one, we have really what water is made up of. And so water, being H2O, is made up of 2 hydrogen atoms and 1 oxygen atom. Now, as you guys are probably aware of, hydrogen and oxygen are both gases at room temperature. One kind of interesting thing is that, all right, those two things separate are gases. You combine them, and at room temperature, water is normally in a liquid phase. And so that's one thing that's kind of unique about you know, water. The constituent elements that make it up have different states than the state of the compound. Another thing that's really kind of mind-blowing when you think about it, hydrogen is an extremely reactive gas. It's extremely explosive, believe it or not. We'll demonstrate this later, but it's really a reactive gas. And then you have oxygen. Oxygen supports combustion. In order for objects to burn, they need oxygen. And so it's kind of weird when you think about this. I have an explosive gas and a gas that supports combustion. And when you combine them chemically, firefighters pour it on fires to put them out. You know, it's really counterintuitive. You would think you would want to keep water as far away from fire as possible. We're looking at the constituent parts. You know, an explosive gas and a gas that supports combustion, but when you put them together, that's not the way it is. The water really isn't explosive. And here's just another example similar to the first one, looking at table salt or sodium chloride. Looking at the two things that make it up, you may not be aware of this, but sodium, a lot of you know that there is sodium in salt, but sodium's a metal. And when I say metal, it's a metal in the purest sense of the word metal. I mean, it's shiny, which is lustrous is a term for that. It is real malleable, which means it's kind of bendy. And in fact, sodium, it's a pretty soft metal. It's really the consistency of, you know, I think of it as like cold peanut butter kind of. So you can cut through it pretty easily with a knife, but it is definitely a metallic element. You can see an example of sodium there. One thing that's kind of unique about sodium is that it is a highly reactive metal. It's so reactive, in fact, that sodium, when you have sodium, if I order some from like a chemical supply company, they store it under oil, because if it comes in contact with air, it rusts instantly, and if you get it wet, it starts on fire. And so sodium is super reactive. Next you see chlorine. Chlorine's a gas at room temperature, and if you look at it, it's kind of this greenish yellow color. Chlorine is super poisonous. One of the reasons why we put chlorine in drinking water and in like swimming pools and so forth is to kill harmful microbes. Chlorine, super poisonous stuff. And so you look at these two things. I have a metal that rusts in air and then starts on fire when you get it wet. And if you chemically combine it with a reactive gas, a poisonous reactive gas, and then it's delicious on French fries. You know, that's just kind of mind-blowing when you look at the different properties of the individual elements, and then the properties of that compound are completely different. That's one of the truly kind of amazing things about chemistry. Okay, back to our pyramid of matter. Directly under mixture, we have our first type of mixture, which is the homogeneous mixture. One thing I want to mention, when you look at this, the first thing you notice, okay, the prefix for homogeneous is homo. When you see that prefix, it's probably pretty natural. The first thing that pops into a lot of people's head, you see the prefix homo and you think of the word homosexual. But you know, that's really okay, because if you think of what it means to be homosexual, then it kind of defines what that prefix means. Homosexuality is when you have, you know, people like where you have men that are attracted to other men, or women that are attracted to other women. And so essentially that means the same. Homo means the same. And so therefore a homogeneous mixture is a mixture that is uniform throughout or evenly distributed. And so that means when you look at it, it looks the same. You can't distinguish different parts of it. It is the same throughout, or uniform. Uniform meaning one form looks the same. And then the other thing that's under mixture is heterogeneous mixture. And so just like we had homogeneous mixture, you see the prefix hetero, you know, it's natural to think like heterosexual. And so heterosexuality is when you have men that are attracted to women and women attracted to men, vice versa. And so that means different or opposite. And so in chemistry, when you're looking at a heterogeneous mixture, that means the composition is not uniform throughout. It's not evenly distributed. Or, in other words, it looks different. You can see different parts in it. It's not evenly mixed or distributed throughout. You see more than one thing. Okay, and that was essentially the end of the pyramid, and so what we're going to do now is we're going to go back and we're going to look at actual examples of each one of these classification of matter things. And so we're going to start over here on the elements. And so the objects you had that were elements were, we have gold and mercury, copper, aluminum, and neon. And if you look at the periodic table, you'll find all these things. You know, early on when you first start, it might be kind of hard to find some of these things because you look at the periodic table and most of the elements, it's probably a little easier to notice their chemical symbols, and we'll get to that. But like gold, you'll be kind of interested to find out early on that, you know, the things like gold doesn't have GOLD in it. Gold symbol is actually AU. And it comes from its Latin name aurum, which means shiny. Just like mercury. Mercury, its symbol is Hg, which stands for hydroargyrum, which essentially means liquid silver. And if you've ever seen mercury, that's really what it looks like. Copper, its symbol is Cu, comes from cuprum, its ancient name. Aluminum and neon have symbols that are pretty easy to figure out. It's just the first two letters. Aluminum's Al, neon is Ne. But all those things are elements. They are the simplest form of matter that can't be broken down by any normal chemical means. Okay, and then moving over to compounds, so we're going to have two or more elements combined chemically in a fixed proportion, and so what's going to be kind of the clue that something's a compound, it's going to have a chemical formula. And these are the examples of the pure substances that are compounds. And so we had salt, ice, rust, and sugar. Okay, and so salt, we kind of talked about this briefly already, but salt, like the common salt you see like on your table you put on food, is sodium chloride, NaCl, 1 sodium, 1 chlorine. Ice, if we're talking about water ice, which is probably what you're assuming is H2O. There are other things that freeze and make crystalline solids, but when I'm talking about ice, usually it's going to be water ice. Rust, once again, that's probably iron oxide, and there's several types. Could be iron 2, iron 3. Let's make it an iron 3 oxide. Okay, so 2 irons, 3 oxygen. That would be an example of rust. Sugar. Sugar, you guys are familiar with like sucrose, which is table sugar. This is the formula for sucrose, C12H22O11. Back from your days as biologist, you were familiar with glucose. That's another simple sugar, C6H12O6. Those things are all carbohydrates, carbon attached really to water molecules. That's where they got the name carbohydrates. But those are some examples of some chemical compounds. Okay, then looking at the homogeneous mixtures, the things we had listed here are like cola or pop, the atmosphere, so just the air you're breathing in, as long as it's dust-free and you're not seeing a lot of particulate matter in it. Brass, you might be interested to find out, you know, people might think, well, brass is it's a metallic element. Well, it's not an element. Brass is a mixture. It's really a combination of copper and zinc is what makes brass. And then milk is a homogeneous mixture, as is sugar water. And so looking at these things like the sugar water and cola, those are really kind of the same thing, where they have water with sugar dissolved in them. Cola also has like carbon dioxide dissolved within it. But the thing is true about them is that they look the same throughout. They're homogeneous. The atmosphere is just a mixture of gases. It's mostly nitrogen, about 78% nitrogen by volume, about 21% oxygen, and then right around 1% carbon dioxide, and everything else is just trace amounts. But like you said, like we've said before, the atmosphere, the gases, you can't see them, and so they are essentially uniform throughout. They look the same. Same thing with brass. You know, you look at brass, a lot of instruments, you know, trumpets, trombones, tubas, saxophones, you know, they're made out of they're brass instruments. And if you look at it, it's that shiny kind of gold-looking metal, but what it is just a uniform mixture of copper and zinc. Milk, same thing. It's really water, and then the stuff that's mixed in throughout it. I mean, you have some minerals and so forth, calcium, but really what's mixed in there is little globs of fat. You know, when you look at milk and you have whole milk, that's where all the milk fat is still in there, whereas 2%, 1% and skim, you know, they've had portions of the fat removed. And then finally, to finish up, we have our heterogeneous mixture. So that was the one where it wasn't evenly distributed, where you could see different parts. And examples of this would be like vinegar and oil. Okay, so think of like an Italian salad dressing. You have to shake it up because of their different densities and their really their polarity, or their one of them is a polar substance, the other one tends to be nonpolar. They are immiscible, which means they don't mix very well together. And so you have to kind of shake them up. But you can definitely see the different layers of the vinegar and the oil. They separate back out. Notice we have the atmosphere when dusty, and so this would be just particulate matter, dust, and so forth blowing around. If you can see it in there, then it doesn't look the same throughout. So it would definitely be a heterogeneous mixture. The next one's sandy water, and so like if you went down to the river and threw a jug in and pulled some water out, you're going to see a lot of turbidity is a word, where you have a lot of suspended solids within there. And so what happens is if you let it set, gravity will take over and pull a lot of that stuff to the bottom. But sandy water is definitely heterogeneous. You can see different parts. Blood, believe it or not, is heterogeneous. Now normally, you know, you might have thought, well, it might have been homogeneous, but the thing is, you know, if you get a cut and you bleed, yeah, when it's first coming out, it looks kind of the same. But what happens is that the blood, as you guys are familiar with from your days of biology, is that there are two kind of portions of the blood. There's the liquidy portion, which is called the blood plasma, and then you have all the cells in there. You have like the red cells, the white cells, the platelets, so that's like solid material. You know, if the blood isn't like flowing or moving through your veins or something, if it's just sitting somewhere, the cells tend to settle out and it kind of clumps up. And so in that instance, I would consider blood to be a heterogeneous mixture. Even though I could probably see the homogeneous, you know, as long as it's flowing and stuff, but if it's just sitting there, probably heterogeneous.